Okay, welcome to Surgical Robotics Lab 8. In this lab, we're going to be doing multiple port placement for a laparoscopic surgery. And what that means is we want to be able to switch between 3 and 6 degree of freedom teleoperation at a certain height threshold. So we're going to be doing teleoperation between the Inverse 3 haptic device and the Mecha 500 robot again. So this will be our setup here. We'll be controlling the robot with this guy. And we're going to want this needle to be pointing straight down when it's above a certain threshold. And once we get to that threshold, we want to set the X and Y location as the constraint, and then operate with 6 degrees of freedom relative to that with the needle tip underneath it. So yeah, and I've taped up the robot there so that you can see it because we've got a lot of gray in the background. So let's get to the activities. So the first thing we have in the lab manual is a list of all of the important files that you guys are going to be seeing. So I've got the folder open here. I've got a few extra things in it that you won't see, but that's just because I have my own completed version. You guys are going to see the SYSC 4206 lab8.m file, and this is what you guys will be filling in the blanks for in the second part of the activity. You'll see the 6DOF inverse kin file, and this is one which you guys are going to have to fill out by yourselves to do the Newton-Raphson method underneath the constraint. As well as a couple other important ones here. We have the needle constrained inverse Jacobian, and it looks like this. It's got one gigantic Jacobian in it, and it takes the inverse. And then we also have the needle constrained forward kinematics somewhere here. And this guy's important because instead of returning the Euler angles and the location of the needle tip, it's going to return the location of the needle tip as well as the point along the needle that is passing through the constraint. And that's a more accurate representation of what we want when we're feeding our information back to the summation block in the Newton-Raphson method. So these are all of the important files. You guys will be calling the forward kinematics and the constrained Jacobian as you go in the 6DOF inverse kinematics script. And then you guys will just be calling the 6DOF inverse kinematics script at some point in the main file, 4206 lab 8. Something else to note, just because I've seen some issues with this in some of the past labs, make sure that you're running your MATLAB scripts from the folder that you're downloading from, because we have all the driver files for the Mecha, or not for the Mecha, for the Inverse 3 in there, and you're not going to be able to connect the haptic device to your computer otherwise. So that's something to look out for. You're going to want to go to Brightspace, download the entire folder, unzip it, and then make sure that you're in the correct folder in MATLAB, which will be up here, and you can see it over here. So it really doesn't matter which order these steps are completed in, just so long as both of them are complete before you guys try to run the entire teleoperation. The way that I've written the manual, you guys are supposed to be completing the 6DOF inverse kin function first. And I've provided some instructions down here so that you can go through and program it. You can also take a look at Lab 7's Newton-Raphson method. There might be a few differences because remember in Lab 7, since we were using the wrist as the bottom half of our Jacobian, we didn't have theta 6 and we had to account for that. That's no longer an issue. Theta 6 takes care of itself. So you could look at that, or you could look at the pseudocode that I've provided up here, and we're pretty much just initializing everything that we may need inside of the loop, and then we're calling the inverse Jacobian function with these input parameters, and then we're updating the current joint angles for each iteration, and then assigning them to the previous joint angles so that we can continue to take the integration in the next iteration. And then, of course, we're updating our error over here so that when we get to the next iteration of the loop, we can check whether or not we're within some reasonable approximation of the joint angles for the inverse kinematics. This might be a little bit misleading while epsilon is greater than 0.01, because if you remember from the previous lab, we've created a vector of our error, and we want the magnitude of that, and we want the absolute value or the magnitude of that to be greater than 0.01 while we're iterating through. So I would take a look at some of the things in the Lab 7 folder if this is at all confusing to you, and try to cross-reference some of the pseudocode with the actual lines of code. So this is basically just abiding by the block diagram that you've seen in lecture, and this time we don't have to account for theta 6 like I said, so it's nice and simple. And in MATLAB, this script is given to you guys. I think that I'm going to take that and make you guys assign it, so hopefully you watch the video. But I've given you guys sort of a line-by-line breakdown. There shouldn't be any giant, conditional branches or loops or anything inside of here. This is just one line for each instruction. So that's the first part. And something else that I've seen in the lab that's been an issue, especially when we're copy and pasting Jacobians. Not that we're doing that in this lab, but make sure that the dimensions of every vector is consistent. If we are using a 6x1 vector, our function has to be calling a 6x1 vector and not a 1x6 vector. The proper use of either commas or semicolons is important because MATLAB isn't just going to be able to figure that out for you. As well as, for anything copy and pasted, make sure it's formatted properly. And yeah, adding semicolons to the end as well, especially for when we're calling the inverse Jacobian function, is very important because the act of making MATLAB display that in the prompt will slow down the program, and we want to be going through this as quickly as possible so that our teleoperation is smooth instead of jittery, if not just altogether choppy and slow. Okay, and then after having completed that, we'll move on to filling in the blanks for the main script. And I've attached some pseudocode for the main script as well, just to sort of illustrate what's going on. But I think that in the video, watching the robot place ports will also be useful to see. We basically want to say that as long as we're above a threshold height, the robot's going to operate with constant Euler angles pointing the needle straight down. And once we've gone beneath that threshold, we want to take the needle's current location and then move relative to that as a constraint. So there are some instructions down here for you, but I've done the mapping there for you as well beneath the constraint. So what I mean by this is where we were just mapping the haptic device to the robot's workspace in the previous lab, which we'll be doing for the 3DOF teleoperation in this one as well. Once we've defined a constraint that we're operating underneath, we actually want to define the location of the needle's tip just relative to that constraint instead. So it's sort of just a relativistic mapping because we're going to be placing ports anywhere we want. So we'll go line by line for the fill in the blanks here. Just like in the previous lab, you're going to define the velocity of the haptic device by some vector. So you could just create a vector and take its magnitude for the haptic device's velocity using its built-in velocity access commands. And you can use that there. And then for the velocity scaling, we want to update the number assigned to the velocity variable so that it maps to some proportion of the robot's maximum joint speeds. And then underneath that, I've just added some conditional branch there saying that if your mapping was a little bit wonky, we're going to bring the velocity down to 99 so that you're not telling the robot to go at 500% of its speed, because it'll go into error there, and then you'll have to go back and forth and reset it. Afterwards, we're going to define the threshold. So we're assuming that if the patient is lying down right here, their torso is just some flat plane parallel to the XY base plane. And we're saying that so long as we're above that, we should enter this condition and map it the way that we did in Lab 7, and then call the 3 DOF inverse kinematics with fixed Euler angles. And then in the else condition, we're saying we're now beneath the constraint, and we're defining the constraint to be the current location of the needle's tip in this global loop starting up here. And the reason we do that and then start a second loop is so that this constraint remains constant. Otherwise, if we kept looping through, we'd be resetting the constraint, and the robot would be moving all weird. So we set our constraint, and then we enter a second loop, and we say that while it's underneath the constraint, we want to map it relative to it, and then call the 6 DOF inverse kinematics, which you guys will have completed at this point. So that's it for what you guys will have to program. I think there was something else to mention down here. Oh, no, we just got the deliverables. So that's all you guys are going to be doing for this lab, and I'll show you what it looks like when I run it. Okay, I'm just going to run my completed code now, and I'll describe to you what I had been saying previously as I go. So when you start the program, the GUI will come up again that you can click on as in previous labs, and you're going to want to start a little bit higher up so that you can start operating in 3 degrees of freedom. And then once you get beneath a certain threshold, which for me is right about there, no matter where you are, your needle will become constrained to that point, and the flange will have to accommodate the 6 degrees of freedom by changing its Euler angles so that the needle will pass through it consistently. So I'll run this, and let's say I want to place a port over here. I'll go like this, and now the robot is changing its Euler angles to pass through the constraint. And now let's say I want to place another port over there. I can tell the robot, maybe that's a little bit far, eh? Place it right there. I haven't mapped this very well. I've now placed a port here, and I can operate with 6 degrees of freedom underneath that. And you can do that pretty much wherever you'd like. It is pretty prone to singularities. But that's the lab activity. So I'll stop running that. Yeah, and it's important to notice that I just created some arbitrary mapping for the needle's tip underneath the cup. That's a great starting place because I got to mess around with it for more than 3 hours before giving it to you guys. So once you've got it all working, you're welcome to mess around with all of the mappings to try to make it as effective as possible. And aside from that, everything is done. So it'll be a formal report for this one. This is also a lab that's worth double what the other ones are worth. So this one's a little bit more important. You're going to want a title page, an intro, just discussing maybe laparoscopy, the Newton-Raphson method, and how we've changed the Newton-Raphson method between 3 and 6 DOF, a little bit about the Jacobian. Maybe that could spill over into the theory section. And then attach some screenshots of your code for everything that you've written, and then just a discussion about what you guys have done and what you observed. And then make sure to also include your references. So that's the last lab for the semester. Good luck, everyone. I'll see you in the lab.